Welcome to a deep dive into OS2. We're going to be looking at some real techie stuff today.
Oh, yeah.
Design docs, programming guides, all the juicy details to see how OS2 actually worked under the hood.
Right.
And maybe learn a thing or two about how it shaped the computers we use today.
You might be surprised.
Definitely. So to kick things off, let's talk about multitasking.
Okay.
Seems so basic now, but
Yeah.
back in the OS2 days, this was a big deal.
Huge. Yeah, personal computers, they were getting more powerful,
Right.
but still nowhere near as capable as like the mini computers of the day.
Yeah.
Especially when it came to multitasking.
So what were some of the hurdles the designers faced trying to make multitasking work smoothly on these early PCs?
Well, picture this, a single user running all sorts of programs.
Okay.
Word processors, spreadsheets, maybe even some early games.
All right.
And every single program wants a piece of the processor, a chunk of that memory.
Yeah.
OS2 had to be the referee,
Uh-huh.
allocate these resources fairly, make sure one application doesn't hog the whole pie.
Sounds like a delicate balancing act.
It really was.
So how'd they manage it?
Well, one of the tricks they used was pipes for inter-process communication.
Pipes.
Yeah, basically channels for data to flow between different programs.
Okay.
So like one program could be crunching numbers, and then another program would grab those results and display them in a nice graph.
So like plumbing, but for data.
Exactly.
Gotcha. But how did OS2 keep tabs on all these running processes?
Good question.
Did they just give them names or?
No, not really. Names wouldn't be very practical.
Yeah, that makes sense.
They came up with this system of PIDs.
PIDs.
Yeah, process identification numbers, basically like a social security number for each piece of software.
Okay.
So OS2 could use these PIDs to manage each process individually, decide when it gets to run, how much memory it can use, that sort of thing.
So like a meticulous record keeper,
Yeah, very organized.
making sure everything has its designated spot.
Right.
But what about when processes needed to team up on a bigger task? I was reading about something called command subtrees.
Right. That gets into the whole family dynamic of OS2.
Or dynamic.
Yeah, parent process could spawn child processes to tackle specific parts of a job.
Okay.
And this command subtree structure let the parent keep an eye on those kids, make sure they were behaving, checking for any errors, even terminating them if necessary.
Like project management, but for software?
Precisely. Delegate tasks, monitor progress.
Right.
Ensure everything comes together smoothly.
Now, did OS2 treat all processes equally or?
That's a great question, and the answer is no.
No.
It had this system for dynamically adjusting thread priorities.
Okay, no, that sounds interesting.
Yeah, so OS2 was designed to be super responsive.
Huh.
So it actually gave a slight edge to threads that were waiting on things like keyboard input or disk reads.
Makes sense.
Those things that can make a computer feel sluggish if they're not handled quickly.
Yeah, like having an express lane at the grocery store for people with just a few items.
Exactly.
Yeah.
Keep things moving. Prevent small tasks from holding up the whole show.
Smart. Now, enough about processes. Let's talk user experience. How did people actually interact with OS2? It wasn't all just command lines and code, was it?
No, definitely not.
Yeah.
While OS2 started with a text-based interface, it quickly moved toward a graphical user interface, or GUI.
Ah, yes, the dawn of windows and icons.
Yeah, it was a big step towards making computers more user-friendly.
So what was the thinking behind this shift to a graphical interface?
Well, a key part of that was the presentation manager.
Okay.
It provided this unified approach to creating graphical elements, you see.
Uh-huh.
So developers didn't have to reinvent the wheel for every single application.
Right.
They could use this standard set of tools to build menus, dialog boxes, scroll bars, all the things that make up a modern graphical interface.
So instead of every program having its own unique look and feel, there was consistency across the whole system.
Exactly. Consistency and ease of use. Imagine having to learn a completely new interface for every single application you opened.
That would be a nightmare.
It would. And by having these standard components, the presentation manager really paved the way for more sophisticated applications.
And for users to actually learn how to use them.
Absolutely.
So this sets us up nicely to take a deeper look into the presentation manager itself,
Yeah.
which we'll do in the next part of our deep dive.
Looking forward to it.
But before we wrap up this section, let's touch upon another important aspect, dynamic linking.
Oh yeah, dynamic linking. This was crucial for extending OS2's functionality.
No, in what way?
It allowed applications to load external code modules only when they needed them.
Okay.
instead of having to include every possible function in their own executable file.
So it's like having a toolbox full of specialized gadgets that you can pull out when you need them,
Yeah, great analogy.
rather than carrying around this giant toolbox with everything all the time.
Right, much more efficient.
But didn't this create some challenges when it came to memory management?
It definitely did. One of the biggest hurdles was figuring out how much memory to allocate for these dynamically linked modules.
Because
You see, different applications might need vastly different amounts of memory for these modules.
Right.
So pre-allocating a fixed amount of space just wouldn't be very smart.
Yeah, it'd be like trying to guess how much food everyone will eat at a party before they even arrive.
Exactly. You're bound to either overestimate or underestimate.
So how did OS2 solve this problem?
They came up with instance data segments.
Instance data segments.
Yeah, these were basically private memory areas assigned to each process that used a particular dynamic link package.
Okay.
So it allowed for flexibility while ensuring that each process had the resources it needed.
So each process gets its own private stash of tools,
Right.
but they can still share some common resources if needed.
Exactly.
But wasn't there a potential downside to this approach?
You're sharp to pick up on that?
Yeah.
Yes, there was a risk.
Oh.
If multiple processes are allowed to access this shared data, what happens if one process accidentally corrupts it?
Uh-oh.
It could potentially destabilize the entire system.
That sounds bad.
Yeah, a single bad actor could bring the whole party down.
So the OS2 designers had to be very careful.
Oh, absolutely. They had to strike a balance between flexibility and stability.
It's amazing how much thought goes into every single aspect of an operating system.
It really is. Every decision has ripple effects.
Now, speaking of resource management, let's not forget about memory itself.
Right.
OS2 had this rather interesting feature called memory overcommit, right?
Yes, it did. And it was a key part of what made OS2 so powerful for its time.
Okay, I'm intrigued. What exactly is memory overcommit and how did it work?
Well, you see...
Back again for more OS2. It's wild to think that we're basically like looking into the brain of a computer from way back when,
Right.
seeing how it all worked to give the user the seamless experience.
And don't forget, we're talking about a time when personal computers were still relatively new.
Yeah, totally.
So OS2 was really pushing the limits of what these machines could do.
Absolutely. So last time we started talking about the Presentation Manager OS2's graphical user interface.
Right.
It's time to dive a little deeper and see how it actually worked.
Right.
What made it so innovative?
Well, the Presentation Manager was much more than just putting windows and icons on the screen.
Uh-huh.
It was a powerful set of tools that developers could use to create really sophisticated applications.
Like?
Think menus, dialog boxes, scroll bars,
Yeah.
even the ability to draw complex graphics and animations.
So more than just a pretty face.
Definitely. It was all about building rich and interactive experiences for the user.
So what were some of the key ideas behind this toolkit?
Well, one important concept was coordinate spaces.
Coordinate spaces?
Yeah, essentially it allowed developers to define the layout of graphical elements in a more abstract way,
Okay.
using units like inches or centimeters instead of having to deal directly with pixels.
Makes sense. That would be a nightmare for developers if they had to recalculate everything every time the screen resolution changed.
Exactly. And these coordinate spaces also allowed for transformation.
Transformations.
Yeah, things like rotating, scaling, even skewing graphical elements to create more dynamic and visually interesting layouts.
So giving developers a lot more creative freedom.
Precisely.
I can see how the Presentation Manager really set the stage for the kind of graphical interfaces we use today.
Yeah, it was a big leap forward.
But let's switch gears back to the world of processes for a bit.
Right.
We talked about pipes earlier,
Right.
but our sources also mention named pipes. How are those different?
Good question. So anonymous pipes, they were great for like one-off communication between a parent process and its children.
Uh-huh.
But named pipes were designed for more persistent connections.
Oh, okay.
They had a unique name that any process could use to connect even across different sessions.
So like a dedicated phone line between processes.
Yep, that's a good way to put it.
Instead of just passing notes back and forth,
Exactly.
when would you use a named pipe?
They were perfect for client-server interactions.
Oh.
Imagine you have a database server process.
Okay.
It could create a named pipe as a way for clients to connect.
Right.
And then client processes could connect to that pipe to send requests and receive data without interfering with other parts of the system.
Sounds like a very elegant solution for creating this reliable communication between different parts of the system.
Yeah, it was.
Now, speaking of communication, our sources also mentioned signals.
Right.
What were those exactly?
You can think of signals as software-based events that could interrupt a process's normal flow of execution.
Okay.
They were used for things like handling keyboard shortcuts, notifying a process that it was about to be terminated,
Right.
or even just sending custom messages between applications.
So it's like a way for the operating system to tap a process on the shoulder and say, hey, pay attention to this.
Exactly. And it's important to distinguish signals from hardware interrupts, which operated at a much lower level.
Uh-huh.
Signals were a software construct, a way for OS2 itself to communicate with processes.
Got it. It's fascinating to see how much thought went into creating these different layers of communication within the system.
It was all about making sure everything worked together smoothly.
Now, while OS2 was clearly pushing toward a graphical future, it still had to maintain some compatibility with the older text-based world, right?
Oh, absolutely.
A lot of applications still relied on the command line and character-based displays.
Right, and OS2 had this special interface called VIO, or Virtual I/O.
VIO.
Yeah, which allowed those programs to run within the graphical environment.
So it's like having a black and white TV set in a world of color TVs.
Yeah, good analogy.
It might not have been as flashy,
Right,
but it's still got the job done.
exactly. These VIO applications, they could even be windowed,
Okay.
but they couldn't take advantage of the advanced graphical features of the presentation manager.
Right. It was a compromise to ensure that backward compatibility.
Exactly.
It's amazing to see how much complexity is hidden beneath the surface of what seems like a simple user interface.
It really is. There's a lot going on behind the scenes.
Every click, every keystroke, every window that opens,
Yeah.
it's all orchestrated by this intricate dance of processes, memory management, and communication.
It's a symphony of software.
But our exploration of OS2's inner workings isn't over yet.
No, we still have more to uncover.
We still need to see how it handled things like storage timing and even those dreaded errors that can happen from time to time.
Right, because those things are just as important for keeping the system running smoothly.
Welcome back to the final part of our OS2 deep dive. It's been quite a journey exploring the inner workings of this groundbreaking operating system.
Right. We've covered a lot of ground.
We have from multitasking and memory management to that revolutionary presentation manager.
Uh-huh.
But now it's time to delve into some of the less glamorous but equally important aspects of the OS2 system.
Yeah, the stuff that keeps everything running behind the scenes.
Exactly, like managing storage handling time and dealing with those inevitable errors.
Right, those pesky errors that always seem to crop up.
So let's start with volume management.
Okay.
Now, it sounds pretty straightforward. We're talking hard drives, floppy disks, right?
Yeah.
What's so complicated about that?
Well, back then you had this whole mix of different storage devices,
Right.
each with their own quirks and limitations.
The joys of hardware compatibility.
Exactly. And OS2 had to be able to work with all of them seamlessly.
So how did it keep all these different volumes organized? Did it just use the drive letters like we're familiar with today, like C and D?
Drive letters were part of it, but OS2 took it a step further.
No.
They used something called volume IDs.
Volume IDs.
Yeah, think of it like a unique fingerprint for each disk or partition.
Okay.
This way, OS2 could be absolutely sure it was accessing the right volume,
Uh-huh.
even if the drive letter happened to change.
So like a double check system.
Yeah, exactly, to prevent any mix-ups.
But all this checking and verifying that must have added some overhead, right? Didn't it slow things down?
Performance was definitely a concern. That's why the OS2 designers made sure these volume ID checks were super fast.
How fast are we talking?
Milliseconds. We're talking milliseconds here.
Wow.
They also had to account for things like multiple programs trying to access the disk at the same time, or background processes doing their own disk operations.
Sounds like they were walking a tightrope between accuracy and speed.
It was a delicate balance, for sure.
Well, let's shift gears and talk about another fundamental aspect of computing. Time.
Okay.
Why did OS2 need special functions for dealing with something that seems so basic?
You'd be surprised how often time comes into play in a computer system.
Really?
Oh yeah, think about things like scheduling tasks,
Yeah.
setting delays, even just measuring how long a particular operation takes.
Right.
OS2 had this set of timer functions that developers could use to build time-sensitive applications.
So a developer could say, run this piece of code every 5 seconds or wait for 100 milliseconds before continuing.
Exactly. But there's a catch.
Mm-hmm.
The timer in OS2 wasn't perfectly precise.
Oh.
There was this thing called quantization error.
Quantization error.
Yeah, basically it meant the actual time intervals might be slightly off.
So it's like having a clock that ticks in these discrete steps rather than smoothly flowing through time.
That's a good way to visualize it.
Was that a big problem for applications?
Not really. For most human-scale tasks, a few milliseconds here or there wouldn't be noticeable.
Yeah, I guess that makes sense.
But it's one of those interesting details that highlights the limitations of working with hardware.
You're right. Even something as fundamental as time is ultimately represented by these digital approximations.
It is.
But let's move on to something a little more tangible. Device drivers.
Okay.
What exactly are they and why are they so important?
Well, every piece of hardware you connect to your computer, the keyboard, the mouse, the monitor, the network card,
Right.
they all need a way to talk to the operating system.
Uh-huh.
That's where device drivers come in. They're like translators.
Okay.
They take commands from the OS and convert them into something the hardware can understand.
So each device had its own specialized driver.
Yes, and that was a key part of OS2's modular design.
In what way?
By separating the hardware-specific details into these individual drivers, the core operating system could remain pretty much independent.
Yeah, that makes sense. It'd make the system much more adaptable to new hardware.
Right, exactly.
But how did these drivers actually get loaded into the system? Were they just part of the OS installation?
No, OS2 did something pretty cool. It loaded device drivers dynamically at boot time.
So it wasn't stuck with just the drivers that came with the OS?
No, it could adapt to whatever hardware was present.
What was the advantage of that?
It made OS2 incredibly flexible. You could add new hardware without having to modify the core OS.
Right.
Which is a huge plus in a world where computer technology was changing so rapidly.
It's like plug and play for hardware.
Exactly. Much easier than having to manually configure everything.
Yeah, for sure. But even with the best designs, things can go wrong, right?
Of course.
What about errors? How did OS2 handle those?
Error handling is one of those crucial aspects of OS design that's often overlooked.
Yeah, I can see how it would be easy to forget about.
But it's essential for creating a stable and reliable system.
So I imagine there are different types of errors.
There are.
Some more serious than others. How did OS2 distinguish between them?
They had this concept of soft errors and hard errors.
Okay.
Soft errors were typically recoverable. Like, let's say you try to open a file that doesn't exist.
Right.
The program could just display an error message and let you try again.
Makes sense. What about hard errors?
Hard errors were the serious ones. They often indicated a hardware failure.
Like what kind of situations would cause a hard error?
Things like a disk drive crash, a corrupted file system, a hardware conflict.
Uh-oh. Those sound bad.
Yeah, these were situations that could potentially bring the whole system down.
Yikes. So how did OS2 deal with these catastrophic events?
OS2 had this special process called the hard error daemon.
Hard error daemon.
Yeah, it was always running in the background, just waiting for these critical events.
Like a dedicated emergency response team.
Exactly. Always on standby.
So what did this daemon actually do?
When a hard error occurred, the device driver would notify the daemon.
Okay.
And then the daemon would take over and try to handle the situation gracefully.
Gracefully. That seems like a tall order when you're dealing with a potential system crash.
It was, but one important aspect was interacting with the user.
Because?
Well, the daemon would need to display error messages.
Right.
And potentially prompt for some kind of action, like replacing a faulty disk or rebooting the system.
But interrupting the user like that in the middle of their work, that could lead to data loss, couldn't it?
It could, and that's why the hard error daemon had this clever trick.
Oh.
It could do a special screen group switch.
Screen group switch.
Yeah, it could display error messages without affecting the currently active application.
So it's like having a separate emergency broadcast system that can interrupt regular programming without messing with the underlying signal.
Precisely. That way the user could address the error without losing any data in their open applications.
Pretty ingenious. This deep dive has been an incredible journey. We've seen how OS2 tackled some really complex challenges.
We have.
From juggling multiple tasks to managing memory and handling those dreaded errors with grace.
It really shows the ingenuity of the OS2 designers.
It does. They were pushing the boundaries of what personal computers could do.
They were, and a lot of the concepts they pioneered are still in use today.
You're absolutely right. As we wrap up this exploration of OS2, I'm left with a sense of awe at just how complex and elegant this operating system was.
Yeah, it was ahead of its time in many ways.
It really was, and it reminds us that the technology we use today is built on this foundation of countless innovations and the hard work of so many brilliant minds.
Couldn't have said it better myself.
Thanks for joining us on this deep dive into OS2. We hope you learned something new and maybe even gained a newfound appreciation for the history of computing.
Thanks for having me. It's It's been a pleasure.